Actually, I'm good if you want to.
All right, everybody, we are very happy to have Maria Zurek from Argonne National Laboratory with us. She's going to give lectures on the physics of the electron-ion collider.
Thank you very much. Hello, everyone. My name is Maria Zurek. I'm from Argonne National Laboratory. That is one of the DOE national labs here in the US, similar to BNL when the Future Electron-Ion Collider will be built, or similar to JLab, which is the co-host lab for the Electron-Ion Collider. Argonne is located close to Chicago. The other lab that is also nearby that you maybe heard about is called Fermilab. And today I would like to tell you a bit about the introduction to the Electron-Ion Collider physics from the experimental point of view. And since we have two lectures, we have this privilege of splitting it into two parts. And in this first lecture, I would like to tell you a bit about how did we get to where we are, what do we know, and what are the open questions we will be answering at the Electron-Ion Collider. Everything from the experimental point of view, from the measurements that happened over the past decades. And I hope that at the end of this talk, we will see where we have gaps. And in the next lecture, we will talk a bit about how can we access or answer those open questions, and what are real, experimental aspects of this, how we can access EIC physics. Okay. Oopsie. Let me start from the introduction. The source of this introduction is my graduation hat. I graduated from university in Germany, Cologne. Is here anyone from Germany or who graduated from? Okay, what was on your graduation hat?
Well, I had a proton on top of it.
Okay.
And some sports equipment around it.
Okay. Everything, I assume, theoretical. I was very experimental, as you can see. So my graduation hat, this is a little Mai. It's a character for the Moomin show. She was very nasty and annoying. I'm not nasty and annoying, but she was kind of, okay, I see some resemblances, okay? And this is my detector. Back then, I was working with lower energy deuteron, and proton collisions at the accelerator called COSY. It was not so cozy, but it was certainly cool. And the detector I was working with was called VASA. This is some of my plots of my thesis. And the sort of tradition in Germany is that when you graduate, your friends and your supervisors, one of them is visible here, another is here, are preparing this hat for you with the highlights of what happened during your PhD. So as you can see, I'm an experimentalist. I run with different tools, mostly screwdrivers. I also measure sometimes some things. And I constantly fight with the detector. I mean, I'm also Polish, so sometimes, the way I speak and the phrases I use are my typical. So every time someone was asking me, how is your PhD going? The number one question you shouldn't ask anyone, right? I'm just like, oh, I'm fighting with my data. Oh, I'm fighting with my detector. So this is me fighting with my detector. Long story short, after the graduation, I did my one postdoc in Forschungszentrum Jülich in Germany, where I was working with the experimental measurement of the proton EDM, electric dipole moment, in the storage rings. I was doing a bit of an accelerator physics. But then I moved to Berkeley, California, when I was working with STAR experiment, when I was trying to access the gluon spin with dijets. And then in 2021, I was hired by Argonne as a staff. And from then, I'm working a lot with the Electron-Ion Collider. I'm interested mostly in three-dimensional structure with jets and semi-inclusive deep inelastic scattering. And I build detectors. And the huge part of my life is to build detectors, understand how they work, design them. and do everything and hope that in 2032, when we will be running, they will be working, and they will be working as we assume. So we will talk a bit about it. But I would like also to know something about you. So today I incorporated like a few Slido polls in the slides. So what you can do to test it is, I would like to know if you are an experimentalist or theorist or anything beyond or between. So this is very easy. You don't need to install anything. Oh, I see some theorists already speaking. Okay. Yeah, I have 4 people. So you can either scan the QR code and then just answer, or you just go to slido.com and you just put this hash, and then you can just, this is actually a poll, so we can just test how many of you are. Okay, 10. Okay, 50-50. Let's see. Let's wait a bit. Okay, we have primarily theorists or theorists in work, both experiment and theory. I'm curious about it. But everyone seems to be kind of decided. Okay, it's good to know to who am I speaking. Okay, not too bad. Okay, so we have primarily theorists with some experimentalists, yay. And then I think one person who is kind of in between. Very nice. Yeah, so, today I will be just briefly touching on the theory concept that has been already introduced in the introduction to QCD and 3D structure of the proton. This was very nicely extensively covered regarding the unpolarized structure, the longitudinal structure, the 3-dimensional structure functions. But today I will show you a bit more how it relates to the experiment, what has been measured. We will look at the very, very first data that emerged from those experiments. And you will be amazed, sometimes how simple those experiments were and how much did they bring and how extensively, complex it started being after the very beginning. Okay, but let me start from this 6 remarkable pictures in the history, not on physics, but history of science in general that I've chosen while preparing to this talk. And I think that all of them, from, double helix photo 51 or Rosalind Franklin, through the beautiful 3-dimensional pictures of the viruses, the high resolution structure of ribosome that was awarded the Nobel Prize, to something maybe a bit closer to us. So both the picture of our universe taken by the Hubble telescope or the very first image of black hole. I think that all those pictures show remarkably that, first of all, humans are very curious, and it's kind of inherent in our nature to kind of go deeper and deeper and understand the structure of everything, the structure of matter that builds me, you, and our whole visible world. But also in general, that in all the sciences, visualizing complex objects is really a key to unlocking deeper insights in advancing our knowledge, especially going to like 3-dimensional structure. Think about the structure of DNA. From 1D to 3D really, brings us more information about how things really work. What are the inner workings of the matter that builds all of us? And this will be sort of a main thought of this talk for today. So let's start from why scattering. I will be covering here a variety scattering experiment, what scattering gives us. So of course, from a very trivial statement that we, cannot use visible light to see inside atoms and protons because our resolution is limited by the wavelength of our probe, to the fact that scattering is giving us a solution to it through the high energy scattering of particles, kind of as a quantum microscope. So in general, how can we probe the inner structure of any matter? Of course, we need a probe, and this probe will be sensitive to a particular type of interactions. For example, electromagnetic, like a photon, or strong, like for example, a proton, when we are colliding protons with protons. And the pattern and the probability of deflections of this scattering gives us several information about what is inside or what we are really probing. So the size and shape, the fact if what we are probing is point-like or has some internal structure, or also other properties like charge or speed, depending one more time on the probe we are looking at, for example, matter. And here you can see a different scales starting from something we can see with human eye or regular microscope, going through the electron microscopy to really see the structure of DNA and viruses that you had some examples on the slide before, to the structure of atom, and really going further and further into resolutions of the order of 0.1 femtometer. So the resolution that gives us access to look inside protons through the fixed target and accelerator experiments with different wavelengths. So large scattering angle in the scattering experiments in general gives us larger momentum transfer and therefore finer resolution. So the shorter wavelength of this what we are looking inside. Yeah.
Like the angle in terms of what, from the scattered electron to the incoming, or the crossing of the E to the P?
I will show you, for example, in the experiments that we had like a simple scattering experiments. When you have a target that we are probing, for example, a proton target, and we are shooting electrons into it, in a very simple experiment that we are looking, for example, into elastic scattering. So we are not breaking the proton. The angle at which in this kind of frame, the electrons scattered from our probe is directly related to the fact how much momentum is transferred to the system, right? And with more momentum, we of course have better resolution power. You can think about it on a high level this way. So what is the plan for today? So plan for today is to think a bit about how did we get where we are. So it will be a historical journey through the proton structure. And then we will go through high-level open questions that are remain. So how the EIC can, and how in general the EIC can address them. And tomorrow, based on it, we will talk a bit about how do we experimentally access EIC physics. So we will do some general overview, and I think we will do the case study for the G1 structure function that reveals the spin composition of the proton. So, lots of people know, okay, we have to measure G1 function. We have something maybe polarized. We are doing measuring some asymmetry, but what do we really have to measure? What detectors do we need? What observables do we measure? How the analysis will look like. You will take your computer, take the data, or even before, try to record the data with the detector, and what would you like to really observe, and what effects you would like, corrections you would like to apply. And then what are the experimental requirements to make it happen? So we'll think about building a detector that will be able to address the EIC physics. What detector requirements do we need? Designing the detector is like, the best thing ever. You just have physics and you have to build a detector around it. Then you sweat, then you stress, but in the end of the day, you're just building something that enables physics, that I think is fantastic. Okay, so let me go a bit right now through the history of the discovery of what we know nowadays about the proton. So as I said, the proton is revealed, but not yet fully understood. Okay, so we start from the historical question. So let's see. Imagine that it's 1950. You are a physicist studying the proton in 1950. What do we know about it, and what is still unknown? It can be super trivial. It can be something complex, whatever you can guess. It's not a history quiz, but take your phones and start typing. What do we know about the proton in 1950? Do we know if it has an internal structure? Do we know if it has a spin? Do we know Anything else? Do we know that it exists at all? Okay, it's positively charged. Wild guess, I would say it's probably good. What else? Come on, it's anonymous, so you can, type whatever you want. It exists, fair enough. Okay, we have something in atomic nuclei. We don't know its internal structure. It has spin 1/2. Okay. Positive charge, elementary, very small. Elementary, very small. Okay, yeah. Bigger than electron. Interesting. It's located in the nucleus, but it could be point-like. It's very dense. Well, experiment. It exists. Fair enough. We don't know the structure of the proton. Good. Fantastic. This is fun. What else? Maybe something about the magnetic properties. Okay, 1950s is quite early, of course. So, any hints towards the internal structure are probably correct. We also have, we are past the first Rutherford experiment, heavier than electron. What is spin? Oh, we have also Q&A. If you wanna ask what is spin, we can have like a hand wavy answer and like how we measure the proton spin. Okay, we have some answers. We have some answers also hinting that proton is fundamental. Kendra.
Hi, buddy.
Kendra, nice to meet you. If you
Right.
Are you Italian, Andra?
Yeah.
So probably in 1950s, you had a good chance to be somewhere, in Sapienza working with other physicists. So it's not, Okay, so this is our understanding on the 1950s proton. Let's see what's up. Rutherford scattering. Rutherford scattering is, of course, very early 20th century. And everyone knows this experiment, but let me point out a few things that you will see later will be pattern in all the scattering experiments from the experimental point of view. So what Rutherford scattering or experiment done? We had a radioactive source with alpha particles of quite low energy of the order of 5 MeV, and we were bombarding a gold foil on it and then measuring the particles that deflected with a very sort of primitive detector it was just like a fluorescent screen. So here there was the question about the angles, right? So we seen sort of cross-section, a probability of measuring particles at the particular angle, and we've seen that it drops rapidly with high scattering angle. We understand that looking into those low cross-sections and the scattering angles that are, very high in this regard, allow us to really, probe what's inside and really look into the interaction of a alpha particle in this regard with a compact point like Coulomb scattering. So basically everything that's said in the low cross-section precision region was what gave us insight into what is inside, what is atom looking like. So, the main takeaway, as everyone probably knows, is that, the observed cross-section really matched the Coulomb potential from a target with a, radius of the order of 10 to minus 14, while the atom size was postulated and was measured to be much higher. So, we learned that atom is empty and it has this central point like Coulomb center. I mean, it's nothing new for you, but you will start seeing lots of patterns in what we are doing. And also shows that the first principle of proving something is of course measuring in the regions that are not always the most comfortable, the regions that were never discovered, the regions of low cross sections and low probabilities. Okay, so we are jumping into 1961. In 1961, actually, these were experiments that happened in 50s and 60s, but before 1950. So you see that only late 1950s, the real more insight into what really proton is kind of emerged from the electron scattering experiment. So we're talking here about the electron elastic scattering. So why are we using electrons? Well, electrons are a clean probe, right? Because they are point-like and they experience only electromagnetic interaction that is well understood. So we have a clean probe to look into proton. Back then we didn't know what else is inside the proton, but basically a proton, a Coulomb-like, point-like potential. So here you can see one of the first pictures. This picture is from the Nobel lecture that the Nobel Prize was given for the electron scattering experiments. And here you can see like a general feature of how experiments looked back then. So in this era, we were talking about energies of the order of hundreds of MeV. So you can see immediately that we go higher in the energy. We had thin targets, and we were using magnetic spectrometers that were allowing us to measure a momentum as well as a position of the deflection through the interactions with the scintillators, and subtracting backgrounds using Cherenkov detectors to measure angle energy and identify elastically scattered electrons. So it's a sort of common picture. You have a beam coming from one side, you have a target, you have some mean of measure the flux, total flux of your electrons, and then you are measuring what is scattered in a simple detector. It can be also changed in the position. You can measure at different angles. So you don't measure everything, you just measure scattered electron. So we said why we are using electrons. So what have we learned? So on the right-hand side, you can see a plot that it's presenting once again the laboratory angle of scattering in degrees versus the cross-section, the probability of observing a scattered electron at the particular angle. You can see here the experimental data that are coming from those experiments. Those were experiments at SLAC and Michigan. There were also some contributions from the MIT. And then you can see 4 different lines. So let's go slowly through it. So we have a first line that shows the prediction for a Mott cross-section. The Mott cross-section describes electron with a spin, half spin, that is scattering of a spinless, structureless point. Then, so you see that we are way off. I mean, on the other hand, you can see that also at low angles, namely worse resolutions, kind of everything agrees, right? So the only way to understand what is going on is going to better and better resolutions, to more and more momentum transfer to the system. Okay, and shorter wavelengths. Okay, so we're thinking, what about, we have to take care, the fact that spin has 1/2 proton, but, it should have probably point charge. And let's see, how it will look like if you would have just a standard Dirac magnetic moment of a point-like particle with spin 1/2. And again, we are looking in the region where we have the most, the best resolution, the highest scattering angles. And we see, okay, it improves the situation a bit, but we're still far away from our data. So people, of course, at the time already understood that and measured that proton has an anomalous magnetic moment. So they say, okay, let's forget for a moment that proton has a internal structure, but let's take a point-like proton, spin 1/2, with point magnetic moment, anomalous, and let's see where we are. So we see that we are also off. So basically, not only from this measurement, but it just illustrates what we directly learned is that nucleons are not point-like. Their charge and magnetization are spread over a few femtometers. There are also experiments that can directly measure, this spread, and this spread is encoded in the form factors, into electric and magnetic form factors that describe how those distributions behave. It also, confirmed that protons' anomalous magnetic moment is indeed due to the internal structure. So here you can see the simple expression for the cross section, where we have this mod part. So as I said, spin 1/2 electron, spinless structure with a modification that comes from the spin and the distribution of the charge and magnetic moment of the proton. What is also important is the following, that when we look into those form factors, the electric and magnetic, I've seen that yesterday at the end of the class about the 3D structure, we had also some overview about the form factors in general. So this was already mentioned, but when we go to the Q² = 0, so, we look in the proton with, you can think about this as 0 resolution, look completely from outside, then, the electric form factor should be 1, so we have charge equal 1, and the magnetic form factor should be mu of proton, which is in the units of the nuclear magnetons. It's just the normalization. So we looked, as in any sort of form factors, into deviation from the point-like scattering. And the deviation from the point-like scattering, any internal structure, will be encoded in the form factors and their dependence on the Q². So from the Q² dependence, in the non-relativistic limit, you can, through the Fourier transform, reveal the internal structure of the objects that we are measuring, of the proton or nucleus, etc. So let's look how it looks like. So why does the Q dependence of those form factor really indicate the internal structure? So here you can see the measurement. This is from a bit later collection of data from the Stanford group. And you can see the behavior of the form factor as a function of Q². So if the proton was very point-like, we said that this form factor should be constant. This was already mentioned on the previous slide. But experimentally, we see that both are falling with increasing Q². And how we can see it? What does it mean that it's falling with increasing Q²? So let's have again the analogy to the light and what we observe and how we can really probe the internal structure. So when we probe the proton or any object with shorter distances, namely we have higher Q², better resolution power, we see less response, right? We see that this form factor is dropping. It means that we are starting probing the internal charge. We are kind of entering the proton inside, if you want to say it this way. So we start seeing the internal charge and magnetization, and we can conclude that it's spread out and not concentrated in the point. Because if it was in the point, however close we will go and with whatever resolution we will be looking into it, it will always look the same kind of intuition. So any follow-up of those form factors would tell us that proton has a finite side and internal structure. Okay, so this was already quite a revelation, and people, of course, and experimentalists don't stop there. If you give us more energy and better resolution detectors, we will start going further and further and further. And I think this is not describing quite well any history of the scattering experiment. So let's look what was happening in SLUG in 1960s. So in 1960s, actually late 1960s, the beam has been upgraded, the detectors have been upgraded, and you can see that right now we can access energies I mean, basically from few GeV to, let's say, 10 to even 20 in the later sort of era of those experiments. And we can measure in kind of similar detector setup. So one more time, we have two arms or one arm of the detector that we are really setting in the fixed angle. We are measuring the scattering. We are making sure that whatever we scatter from is in, well defined in our target, that we measure flux of our particles, and that at the fixed angle we are able to detect electrons. What does it mean? So we have to know the energy and position of this detector. We know that these are two, variables that define how the detector is reflected, and we also have to make sure that we are distinguishing them from other background particles for which we have Cherenkov detectors in this particular setup. As you can see, this is a human being. It was quite big detector. Still simple, but already quite a bit of an upgrade. Okay, so what have we learned from SLAC, where we are? We are entering a regime of a deep inelastic scattering. Okay, we have two words close to the scattering, deep and inelastic. Why inelastic? Well, as opposed to elastic, where we basically had just electron-proton going into electron-proton, we can either observe different resonances that has been produced, or basically break proton into a very complicated final state with lots of particles. So this is inelastic, right? Is opposed to elastic. Deep. Well, as you can imagine, deep, because we have enough resolution, we have enough Q square, enough energy in our beam that we can go deep into the proton, so start looking into resolution smaller than the proton radius. And as it was introduced yesterday, the cross-section for the deep inelastic scattering can be written as a function of two structure functions. And when you look into this formula, it looks actually quite similar to what we had for the elastic scattering. So you have some structure functions, you have the angle dependence, right? So what physicists do, of course, they try to check if this depends on the angle of scattering or not, or depends on the Q square or not. So as we said, if we are looking into the cross-section, for example, and we are checking how it changes, or into those structure functions, and we check how they change with the resolution, with the angle, if we observe a strong drop as an elastic scattering, we know that a proton or a nucleus that we are probing has an eternal structure. When we see something like this, we start thinking, maybe not. So we have enough resolution to go inside the proton. So effectively, people were concluding, okay, we are looking inside the proton. What's shown on this plot is also SLAC experiments, actually a collection of one. It's one at the very beginning of the whole campaign, so it's 1969. And what we are showing here is the cross-section divided by the mode cross-section, right? So as we said, mode cross-section, point-like, spin 1/2, electron on the spinless point-like proton. So we divide, right? And what we see is that basically, we have some dependence at low W's. I would say about the W's in a second, but basically when we go to the regime that we are really in this deep inelastic scattering mode, we see some dependence, but it's, nothing like an elastic scattering. So basically we see that the dependence is very, very weak. So experimentally, we start looking into so-called scaling. So how the structure functions that we are measuring scale with the resolution, with Q square. So what we observe is that at this, extent of the experiments, The structure functions show scaling. I will show you in a second on the other slide. That hints that we are scattering of point-like constituents. And this is before parton model. This is just the foundation of the parton model. This is before about knowing anything about quarks, right? There were some postulates that, quarks can exist, but it's just sheerly experimentally the same type of experiments, the same type of scattering. We see very, very weak dependence. We see scaling. Later, as I said, right, all of this kind of binds together into the picture of the parton model, sort of suggested by Feynman, into the identification of this point-like constituents as quarks, into development of the QCD, et cetera, et cetera. But these are really, the first fundamental hints what is going on inside the proton. Okay, so here to show you some of those results related to scaling, we are talking about the momentum transfers of the order of 6 to 8 max GeV at x equals 0.25. So omega is 1/x for just to jumping a bit forward before the sort of refresher of the kinematics at different angles. So what we generally observe is that at large Q squares at which we can probe the F2 structure function. So the structure function that in sort of, leading order interpretation just measures momentum of the distribution of quarks, the momentum distribution of the quarks inside the proton. So basically leading order interpretation of the parton distribution functions, PDFs, weighted by their charge square. And F1 is related to the transverse response to the transverse photon. So you see that this is basically scaling, that F2 at this measurement, this particular resolution doesn't depend on Q squared. The other important relation that could be tested is the Coulomb-Gross relation. So which generally shows it is related to the fact of the helicity conservation in the interaction between the longitudinally or transversely polarized photon and half or one spin quark, that basically if this relation holds to some extent, then we are probing a system that has spin 1/2. And you can see that one more time with this particular resolution as a function of Bjork and X that can be interpreted in the infinite momentum frame as a fraction of the proton's momentum carried by the struck quark. Nowadays we know quark is flat. So it also hints on the spin of these point-like objects that are inside the proton. So slowly, we are revealing everything. So let's do a bit of the refresher regarding the kinematics of the BIS, because it will be important later for any considerations regarding what we are measuring in our detector, where we are, etc. So we talked a bit already about the Q square, which is basically a resolution, the 4 momentum transfer squared, or the resolution scale. So here we have a simple picture of the electron with, or a lepton in general, with a 4 vector with the energy E and the momentum K. And then you can see the deflected electron over there and the deflection angle. Here you can see also schematically the proton, the virtual photon, that it's carrying the 4 momentum Q, and everything will kind of escape this reaction apart from the scattered electron. So we talked about the momentum transfers. That'll be very important because it sets our resolution scale. We also have the energy transfer. So difference between the energy of the electron and the scattered electron, that it's important. And then the Bjorken next that we just defined as a interpretation of the fraction of the momentum of the struck quark. And this is also the scaling variable. So the variable you will see later, we are looking at into the F1 and F2 structure functions. We define inelasticity, so the energy transfer to the proton divided by the initial energy of the electron, that tells us how much energy is transferred. So how inelastic our interaction was, right? So once again, deep inelastic. So the higher Y, the more inelastic we are. And last but not least, so the invariant, that it's really important to understand what kind of reaction we are measuring and what we are dealing with. And in any experimental data analysis, you can be looking into either the energy of the scattered electron or W. W is the invariant mass of the hadronic system. So basically how much energy, how much phase space you have for the production of anything else in the reaction. So you can think a bit about it also as a missing mass of everything apart from the electron that has been produced. And what's important is that in any experiment, any DIS experiment, and I'm talking here only about DIS, like a shear experiment when we measure just the deflection of the electron, or we can measure alternatively the final state, but to just describe DIS, not semi-inclusive, not an exclusive reaction. We just need to measure either the scattered electron energy and angle, so a bit different from the simple Rutherford experiment. And these are experimentally very easy to understand because this is basically what you measure in your any scattering experiment, or any of those two, Yx or Q square, and they are related, by this known relation, and they are Lorentz invariant. So when you think, okay, what does it mean experimentally? Well, I scatter something, I have to measure it. If I have very, high scattering angles, it means that I will have high resolution, but then the cross-section and this angle is very low. So I have to be very precise. I have to have also, enough luminosity, enough flux of the particles in my beam to measure at those angles, etc. And I have to have high enough energy to get to Q square, right? To the required resolution. So angle and the energy of the outcoming electron. So let me show you a bit about the W that I mentioned. So we said that, okay, we are measuring, you have any experiment. In this experiment, you're just throwing the beam of your electrons into some target, let's imagine. Or in a collider-like experiment, I'm smashing electrons with protons on electrons with heavier nuclei. And then, I measure some angle and energy, and how the heck do I know what have I measured? What is this, right? You don't want to measure everything. If you want to be sensitive to a particular reaction, or you would like to, for example, test your detector and calibrate with the elastic scattering, or you are interested into the resonances region, or you are interested into semi-inclusive deep inelastic scattering, or, any other, regions in between. There are several methods you can identify them, and this is, this is an example of the experiments of 10 GeV, and you can see what's happening when we are going higher and higher with W, right? So we can see an elastic peak when W is equal to mass of the proton, and just to be clear, this is scaled by factor of almost, it's 8.5, because the elastic scattering cross-section is really high and very peaked at the proton mass. And then, so basically it means that proton doesn't break up. And then you go into the resonances region, have, for example, first resonance of delta resonance. So you still have, you break, you have inelastic scattering. You don't have exclusive sort of processes here, but you are not going into region that you have really, the deep inelastic scattering. And this is, this is where you go higher when you have this inelastic region, the sort of continuum region. Usually people say 1.8 to, let's, don't be too picky depending with which community you are talking to. But in general, you are going into the region of the continuum, the region of deep elastic scattering, and really this region revealed the most. I mean, I'm, not saying that like resonance region is not interesting. It's interesting, but when you look into the history, we are going there. We are getting there into the, this very deeply inelastic region. If you go further and further, to mention, maybe some of you, is thinking about harmoniums and botoniums in the context of EIC. The further you go, you can also have other resonances that are reflective of different processes. Okay, well, how are we with time? Well, could be better, could be worse.
So flexible.
Okay, so now, I think I missed some plot. Anyway, there's supposed to be like a beautiful Feynman diagrams of this, how gluons splits to quarks, etc. Imagine that they are there. I don't know what happened.
You put it on the board if you want to.
That's okay.
I will do it. I will do it when I submit it. Okay. So we were saying, yeah, we cannot throw. We would have to, smash them with electrons, okay, to just see what's going on. Anyway, gluons and scaling violation. We were, as of now, it's 1960s, 1970s, 1990, the Nobel Prize is given for the deep inelastic scattering. And then we are kind of thinking, okay, are we really seeing the scaling of the structure functions as a function of the momentum transfer? What we are doing, of course, we are going to even higher energies to ultimately reveal the internal structure of the proton. And this plot is the legacy of the Hera experiments. I will mention it also on the next slide, like what Hera really gave us. But to kind of have a continuity of the discussion here, we are talking right now about gluons and scaling violation. So we had a Parton model. We postulated quarks. I mean, not we, Feynman did, right? But, so we are kind of there. But then, of course, physicists say, no, we want to go deeper and deeper inside the proton. We want to really see what's going on. And we are looking into proton structure function as a function of Q squared. So what is on this plot is actually not a log scale. That is actually good, because often this plot is shown on the log scale, and then it's a bit distorted of the effect. But what you can see here, this is one more time, momentum transfer Q squared. This is proton structure functions F2. Think, PDF leading order. And then you are going lower and lower and lower into S, into the momentum fractions. And then what we know from a modern, nowadays, from a modern picture of proton is that the deeper we go, the lower momentum fractions we probe, the more and more gluons we have. Now we know. So of course, deep inelastic scattering probes directly the behavior of quarks. So again, people look into it and say, we see the scaling violation. The scaling is violated. So clearly at high Q square and very low X, it is not flat. So it was an indirect hint, sort of a sign of the QCT dynamics at play, basically the change. So what happens is the following. So quarks can radiate gluons. Also, gluons can split into quark-anti-quark pair. So if you would like to think one more time intuitively about it, is if we go to very low X's, so very low momentum fractions, we have lots of gluons. And those gluons can split into quark-anti-quark pairs. When they split into quant and anti-quark pairs, since we are sensitive to quarks in DIS, we have the increase with the better and better resolution, because we start really resolving those gluons splitting to quark antiquark. This is like hand-wavy experimentalist explanation of next to leading borders, okay? So trust me, it's true. I'm joking. Similar thing can happen, is maybe not super visible here, but when you go to higher x, and you have a quark that is radiating gluon, the momentum of this quark is shifting towards the lower momenta. So then you would see that the behavior is slightly tilted in the opposite direction. So indirectly, scaling violation gives us kind of hint of the gluon distributions through the well-known QCD evolution that I think it was quite well described on the QCD introduction class, I think first on Monday. So once again, scattering experiments, indirect hint. Of course, there were also experiments that directly proved gluons, and there were experiments that show the jets from gluons in Petra, etc. But I cannot cover everything, so I'm just showing here some things. And then again, this is a very nice example of modern PDF particle distribution function fit of different species of quarks and the gluons inside the proton. This is, of course, a modern picture, but you can see the reflection of what is going on when you are going from the small scale to the high scale, right? With growing gluons and the picture of the less visible bumps of UND quarks, and how much those scales of quarks sort of radiating gluons are growing, as well as the increase of the U D bar and S bar. So the those quarks splitting into those gluons splitting into quark and anti-quark pairs. There will be the whole session about the PDFs. So this is just me kind of hand-wavy linking the previous plot to this plot to understand what is going on. And you can see how it behaves at different scales. So at better resolutions, like low X, better resolution, we can resolve these things that sit at very low X. Okay, so here's the one slide summarizing the legacy of Hera I mentioned. So, we talked, it is just to sort of close the discussion about the history and where we are. And it's not that I want to make it short for Hera, because there's a lot of things that happen. I think, that this also nicely bridges to the EIC. So we talked about a very simple scattering experiment with target-like kinematics. So we are smashing electrons to the target, but to access even lower values of X and higher Q squares, it's profitable to go to the collider-like kinematics. So here is the complex of Hera and Daisy, Germany, that ran between 1992 and 2007 and collided electrons with protons at high energies, roughly 300 GeV. And the previous plot that you've seen on the previous slide, so this sharp rise of the F2 structure function at low X with increasing Q square was, this decade of measurements. So Hera revealed really the scaling variation F low X, not only with the collaboration with other experiments, of course, but had a very significant input into it. I mean, you had to access low X, and to low X, you have to go to high energies. It gave us confidence into deep lab evolution, and provided also the really first, I don't want to say first, but provided a, really global fits of modern, with modern extraction of the PDFs of particle distribution functions, and the example of it at, quite high scale, you can see here. So these are just fits sheerly from the Hera data. And much more, I'm not touching here upon everything. There were also lots of things happening with the heavy flavor PDFs and diffraction and jets and low X physics in general. But basically, it laid the groundwork for future precision studies at the EIC. And, here I want to mention that Hera was an unpolarized experiment. So it gave us a lot of insight into structure functions that are unpolarized, the PDFs that do not track any correlation with the spin of the proton. And this is what I also want to bring as one of the motivations for the EIC is the discussion about the proton spin crisis or puzzle. I think, right now we are in the puzzle mode. In the 90s, it was really a crisis mode where we have measured a structure function, the polarized structure function, and we will tell tomorrow a bit about how we can do it, how we can measure something polarized, how we can extract G1 based on a simple, experiment, a scattering experiment with polarized beam. And this is also non-trivial and polarized targets. And what we have observed, or what, back then I was not born in 1988, was that in general, first experiment was basically consistent with 0 within the uncertainties, yay. But then, uncertainties improved. And over the years, we've seen that roughly 30%, 25 to 30%, depending on, of the extraction and the range of X, we are able to extract the proton spin comes from a contribution from the spin of quarks. And what we are measuring, or we are probing, we try to access the quark helicity distributions. So similar to PDFs, but longitudinally polarized. So those distributions tell us to what extent spin of a quark of the particular flavor or a gluon that sits inside the proton has spins aligned with the direction of the longitudinally polarized protons. So basically, how much of the spins of those quarks or gluons contribute to the overall proton spin. One more time. LO, QCD, quark parton model, what, explanations like the most. So it, of course, shocked the community in the beginning. We called it proton spin crisis. And I said from crisis, we went to puzzle, but it's still a puzzle. So, here, of course, the EIC will play the central role. Here, I will just flash several. It's a good picture of the current status of this, where we are with the longitudinal spin structure. So longitudinal as opposed to transverse, in the sense like how much of the proton spin really comes from the quarks and gluons and their orbital momentum, because this also, so the movement of quarks and gluons inside the proton. So here you can see the summary of the delta U and delta D. So the delta just means, the contribution from the U quark and D quark. So from the structure, from the polarized structure function, the longitudinally polarized, the helicity. So here you can see that as of, now with the current experiments we have, those experiments spanning from, let's say, 10 to -3 in X to quite high X's, from the experiments like Compass or JLab or Hermes, we know it, not ideally, but quite well in this X region. We also can look into the C-quark polarization asymmetry, namely how the anti-U quarks are polarized with respect to anti-D and how do they contribute overall to the spin. And then here are our gluons. And the insight to gluons, basically from the current measurements, from the semi-inclusive deep inelastic scattering, all DIS experiments, those indirectly through the scaling violation, right? So we measure scaling violation in polarized experiments, it has to be polarized, and we are looking into how much gluons contribute to our spin. Well, it's not the best. We still, we managed to shrink the uncertainty quite a bit in the region from, let's say, 0.05% to 1 in X. And those insights predominantly come from the proton-proton collisions and longitudinally polarized proton-proton collisions in rig experiments, measurements with jets or direct photons or digests, etc. But when you look into the very low X, where all of us, are super interested about for sure because of the EIC, as you can see, we are still, you know, in a quite bad shape. And here you can see integrated numbers. Okay, this is sort of a recap. What have we learned? I will not go through everything. I will just mention, because I just said it, but I will just mention two things that I didn't say here, but we also, you know, are quite interesting. So if you want to, you know, read a bit more about, like, historically, if you are interested in this kind of aspect of history of physics, there's also nice experiments that are and sort of conclusions that are inferred from the DIS with neutrino scattering that tell us about the fractional electric charges. And there is the whole area that we will touch a bit more about in general, especially in the polarized case, but also in the unpolarized too. I mean, these are very unique for the electron-ion collider, are related to what we call the EMC effect. So basically how the quark distributions are modified inside the nuclei. And in general, what is the impact of the fact that the proton I'm probing is not a free proton, but is the proton that sits inside a nuclear matter, right, in a nucleus. Okay, so I see that I'm running, not like a running coupling constant, but like I'm running out of time. So okay, I will just flash this saying that, you know, this is kind of the evolution of the picture of the proton, starting from, you know, very basic constituents in 1980s into a really complex systems of quarks and gluons that are constantly interacting between each other, that are splitting and radiating, that have free net valence quarks, but also, you know, zillions of transient quark and anti-quark pairs and zillions of gluons inside. And now, you know, one of the main questions is how out of this mess, because if someone would ask me what the proton is, I would say it's a mess. How out of this mess, really very basic fundamental properties, I would say borderline, you know, macroscopic or having influence into macroscopic world, let's say properties of protons kind of emerge. How from this dynamic system, things like mass or spin, you know, emerge through these intricate interactions between quarks and gluons. And I will leave it here. I just want to say that this is not the complete list whatsoever. These are just, you know, some highlights. And as of now, and as we are moving forward, we'll move to the discussion of the main goals of the electron-ion collider. We can certainly say that the 3D pictures, especially of gluons and C quarks, are really largely the uncharted territory. And as I mentioned, really understanding the connection between the dynamics and the emergent phenomena like spin and mass. And to finish, I would like just to, you know, start or I finish with this and we can start tomorrow. Because if you are excited about something specific about the EIC, then we can talk a bit more about it tomorrow. So it's kind of a wish list. So the question is, what do you think is still unknown about the proton that, you know, EIC will be able to sort of address? And I mentioned already spin, but you can go in any direction you want. Or, you know, what mystery you're really sort of looking forward that EIC should help solve. So I will leave this poll open. You can start replying right now, or if not, we start from it tomorrow. So thank you very much for your attention. I hope you participate actively. And yeah, I didn't manage to go through all the motivation of the EIC, but we will start from this tomorrow morning. Thank you very much.
Thank you.
I think we have a break right now, but if you have any questions or, you know, please participate. I mean, Alex, I can imagine that you have very specific answer to this question.
No, I'll try to participate. Thank you for this very interactive lecture. Questions? Good.
So when we talk about 30%,
30%.
That's for the valence quarks, right?
It is for all, yes. I mean, you can see it as the, it's actually it's the integral over all quark contributions to the proton spin in general. Then you can see that there is a small asymmetry between quarks and antiquarks. But, the question is, if we, integrate over x equals 0.005, do we talk still about valence quarks? Yeah, there are free net quarks, but it's generally integration over all quarks inside the proton. So if you would take delta x in some region, it would be just this delta x integral over this b.
So are we able to tell how that 30% is more specifically spread out? For instance, the two up quarks have this much and the down quark has this much. Like, is that?
Yeah, so we can say based on this dependence. So basically how you are presenting the helicity distribution, you present it as a function of x. So it's flavor separated, and you can do it flavor separate. So if you do just simple DIS, it will be either all quarks together, or you can be sensitive to a particular, regions of the proton, like more sensitive to gluons, right? Or more sensitive to C quarks. But in general, you probe everything together. But if you start looking into observables, where you also detect your hadron in the final state, like for example, semi-inclusive deep inelastic scattering, you can get some, predominant sensitivity to particular flavor of the quark. Or you can go to the production of, like, for example, W boson and look in the asymmetries there, because, this production would also couple to a particular, the U and anti-D or D and anti-U, right? So as you can see this is the extraction for all the world data currently. We can split it. We can see how much it comes from U and D with the particular, X, DX region. But, I think that the grand question is, it's up to, everyone can ask this question. Everyone can say what's interesting or not is, how everything contribute. You can look also at the, like asymmetry, how much, this over X, so it can be a bit misleading, but in general, it says, how much more delta U is there versus delta D bar, and this is in this surely the C part. So you can slice it and dice it, right, in all the way, and you can get sensitivity to all those components through a different, particularly also reaction channels that target those. If they're not, I would be around. So like if you prefer to, have like one-on-one discussion, it's also fine. Or up to you.
Question here.
Just to have an idea, could the rest of the contribution of the spin could come from the mechanical properties then?
Well, in the sense of mechanical properties, in the sense of like, we have a spin decomposition, right? So we know how we can decompose the proton into the spin into particular reference frame. Like, for example, we have a Jeffy Manohar decomposition that, works in the infinite momentum frame. And then we can, we know that there should be a contribution from the, just like motional contribution, right? Through the angular momentum. And this is basically mechanical, if you want to think about it this way, right? And you can probe also, contribution to the proton spin if you talk about, the particle unrelated to the orbital momentum through observables that you would probably more traditionally think about, like mechanical-like properties. So if you go to like deeply virtual Compton scattering, some observables and reactions that are exclusive, that usually, are related to those, mechanical form factors, right? You can also get access there, and most probably it is. And I have a remarkable plot that I will show tomorrow about how little we know about this part. Like we really know almost nothing.
Just a couple announcements. I'd like to introduce Bjorn Schenke, who's going to lecture tomorrow. He's one of the co-spokespersons of the SURGE collaboration, so he's fair game for questions. during coffee breaks, and pass around the jump drives for the tutorial this afternoon. And then if I could see Diana, Alan, Jan, Vincent, and Mateus for a quick photo right now, enjoy the coffee.
Right.
And let's see, quarter of, is that
Quarter to
good?
11. Yeah,
All right,
exactly.
yeah, have a nice coffee
Let's
break.
thank Maria once again. Oh.